So now that we've talked about all these different operators in the Project Reactor's Flux class, let's go ahead and turn our attention to a case study that pulls all the pieces together. It's a two-part case study. The first part shows how a whole slew of these newer Flux operators, plus some older ones, are used in order to create, reduce, multiply, and display big fraction items largely in an asynchronous way. And so, as usual, we also show off some mono operators as well as some operators that come from things like the the Project Reactor Schedulers class. And as always, you can find this in my GitHub repository. This time it's the ex3 project in my Reactive Flux folder in my live lessons GitHub repository. We're now over in project ex3 in my live lessons GitHub repository that deals with the reactive flux examples. And let's go ahead and take a look at this example program. As you can see, we've got a bunch of different methods here. And so we're going to take a look at the ones that do exception processing here. These are the ones that are registered with the async task barrier to deal with exceptions. And then we'll come back and talk about a couple other examples that use combinations of Java streams and Java Project Reactor mechanisms. As usual, after all these operations are registered, we run everything in the main thread of control using the async task barriers run tasks method, which then blocks the main thread until everything is finished. So let's now go ahead and talk about the implementations of these methods. We'll start out by taking a look at test fraction exception 1. And this is going to show how you can use the on-error resume operator. So what we're going to do here is we're going to have a list of denominators, 3, 4, 2, 0, 1, 5, and then we're going to make ourselves a little function variable here that's going to log an exception and just return an empty flux. So very simple fallback behavior. Keep going, but stop any further processing of the flux, just return an empty flux. So here's what the program looks like. We're going to go ahead and take that list of denominators and turn it into a flux of denominators. We're then going to go ahead and perform the creation of a big fraction with a random numerator and one of the denominators. And if the denominator is 0, of course, this value of call is going to throw the arithmetic exception, as it well should. Now, what we do here is we use the on-error resume method, which says if an exception occurs, log it and return an empty flux, which just says bail out at that point. Don't throw away what's already been processed, but anything that came after that will just be ignored. We're going to resume by ignoring what came later. Now, the other thing we do here is we use the on-error stop method that says, I really, really, really want to stop at this point. I don't want to let some other on-error continue operator override the behavior here. So I really want to bail out, please. And then what we do is we collect the non-empty big fraction elements in this flux stream into a list. And then we go ahead and we take that list and we sort it and print it. And this, of course, uses our clever technique we've looked at multiple times now, where we're going to simultaneously quicksort the list in parallel with heap sorting the list in parallel. So we use the mono from callable factor method to basically quicksort or heap sort the list, and we run those in the scheduler's parallel thread pool. Whichever one of those things finishes first, we're then going to go ahead and use the mono first with signal operator, which takes those two monos, and whichever one finishes first, we're then going to go ahead and use this local consumer variable in order to be able to print the results out from that sorted list, whether it was heap sort or quicksort. We don't know, we don't care. We just take whichever one finished first. And at that point, we then tell the async task barrier, we are done. So it returns back here. And that's a flag to the async task barrier that we're finished. So that's the on-error resume mechanism. Let's now take a look at a different way of doing things that we use on-error continue. So what we're going to do here is have the same input, a list of denominators that include a 0. And we're going to have, this time, we're going to have a by consumer variable called log error and continue. And you can see what it does here is it's just going to go ahead and log the exception message again. The Flux stream looks very similar. We start out with a list of denominators, turn it into a flux. Then we go ahead and do value of, which is going to throw arithmetic exception when the denominator is 0, which, as you recall, occurs on the 4th element here. And what we're going to do this time is we're going to catch and log the arithmetic expression, the arithmetic exception, and then just continue processing. So we're going to kind of log what happened, but we're going to skip over it, and we're going to go ahead and continue processing the rest of the elements that are not throwing the arithmetic exception. And then we collect the results into a list and sort and print the list. Then the third approach we're going to do here, this one actually uses asynchronous processing, just to be different. And we could have done that for the earlier approaches. We just made them synchronous to make them a little easier. Again, this time we're going to have an error handler that logs the exception message. But unlike the earlier approaches, which either terminated the rest of the processing or just skipped over it and ignored it, this time we're going to convert arithmetic expressions into the value of 0. So we'll get back to 0. Same set of denominators as input, same overall structure of the stream, except now we're going to use flat map. So if you look before, we used map with a single thread. Now we're going to use the flat map concurrency idiom. And in a background thread running out of the parallel thread pool, we're now going to go ahead and do this value of operation, which will generate the arithmetic exception when the denominator is 0. What we do here is we use the on-error resume method, which is just going to convert that arithmetic exception to the value 0. And then we go ahead and do the operation, multiply it, and so on. And when we're all done, we're going to filter out anything that's 0 or not. We're going to only let things greater than 0 go through the filter, collect the results to the list, and then sort and print the results. So given all that, let's go ahead and run the test program. We're just going to look at the first 3 outputs here. So you can see in the first approach, we got the divide by 0 exception, which is the arithmetic exception. So we only processed 3 of the total 6 denominators. For the second test, which used the on-error continue model instead of the on-error resume model, this time we once again caught the fact that divide by 0 occurred, but we continued processing the other non-zero denominators. So we had a total of 5 outputs. And then the final approach, where we did things in the background using the parallel scheduler and the flat map concurrency idiom, once again, we catch the divide by 0 exception. And but what we did in that case was we produced a 0 result by using on-error resume. And so what we ended up with was 6 computations, but then we filtered out anything that was not greater than 0. So we ended up with only 5 results when all was said and done. So hopefully that helps to give you a good feeling for how these different operators work in Project Reactor. And you can use them effectively in your own code if you write code that requires error handling using synchronous or asynchronous Project Reactor features.